Hi, this is a quick little video on a relationship between the graph in a position versus the first derivative and second derivative. Oftentimes we think of these as the velocity graph, a position graph, a velocity graph, and the acceleration graph. So let's see what it looks like when we actually put it to use. Let's say we have the function f of x equals negative 5x squared plus 18x plus 1. Now we know from our regular math classes that anytime there's a negative out front and it's squared, it's a parabola and it's negative, so it's facing down. So we have something like this going on, and what we want to do is we want to be able to graph it and use some of the other techniques that we've used in the past, using our first derivative test to find maxima and minima, and then graph it on a 3-level graph or a 3 different system graph, so we can see what the relationship is between those. So again, first step, what we want to do is take the first derivative, that's negative 10x plus 18 using the power rule. We set that equal to 0. We get negative 10x is equal to negative 18. And finally, we divide by 10, and 18 over 10 reduces to positive 9/5. So then we take the derivative one more time. The derivative of negative 10 is just negative 10. The 18 is a constant, and so that goes away. So I'll start off here in the bottom because it's a little simpler. When we have f prime of negative 10, that's just a regular horizontal line at y equals negative 10. Now to see what we have here, we can put together a line test or a graphical representation here, linear representation. If I have a critical point here at 9/5, then again I want to check on either side of it to see if my slope is telling me the same story as what I should have in the graph. So we conclude that if we put a 1 back into our derivative, we will end up with a positive slope. And that's what we see here, positive slope. If we put in a 3, okay, in here, we will get a negative slope. And that's exactly what we see on the other side of the 9/5. All right, so now let's take a look and see what the graph looks like of each of these three. Now remember, we are so used to graphing the position function that sometimes we don't really understand what the velocity function or the velocity graph will look like. And I'm going to kind of explain that to you in this video. All right, so we have the original position function. We know that at 9/5 and about 17.2 it has a maximum, okay? And then if you graph it, you will notice that at about negative 1/2, maybe a little bit touch more, and at about 3.6 or so, I just drew it about 3 to keep it somewhat simplistic for us, just so you can get the idea. Now this is the position of some particle and where it is. Now if we want to know its velocity or draw a velocity graph, then we have to think of the graph in a different sense. In this case, the x values, right, in here the x is plugged in and it's going to some y associative value. Here now, the x determines where it is in reference to velocity, and the y value is the speed or the magnitude of that velocity, meaning the higher I go up in y values, the steeper the slope becomes, right? So if I'm at 1, I'm at a very low slope. And if I'm at 18, then I'm at a very steep slope, okay? So this is the slope and how steep it is, right? And the x just tells us in what reference to that value. If I plug in an x value into the first derivative, it will give me a positive or negative value of a slope, okay? So again, this is position, this is velocity. If I'm at a negative low number like negative 1, negative 2, negative 3, those are very low slopes. Think about a slope of negative 1. It's over 1, down 1, right? So if I have negative 2, it's over 1, down 2, right? So rise over run. getting steeper, -3, -4. But 18 would be over 1, down 18. So we have a very steep slope. So that's what that is marking. And so this is the position graph. This is the velocity, or the first derivative graph, and then this is the acceleration. Now, again, let's see how they relate. We have in this first situation our position graph. Well, what do we notice about the slope all the way up until we get to the critical point, right? The slope is getting less and less steep, more and more steep as we go down. So, this is relevant to here on this graph. We are getting higher. The further we go in negative x values, the steeper the slope becomes, right? The steeper the slope becomes, it's going to go wildly down this way. However, as we go towards 9/5, the slope starts to decrease. Again, the y values are the value of the slope in terms of its steepness, not necessarily the position. So as this graph is coming up, we notice that it's getting less and less and less steep. Okay? Think about climbing the stairs or so. Would you rather climb that set of stairs or that set of stairs? Okay? Or running up the hill. All right. I do a lot of mountain running, so we see that sometimes. We look ahead and we go, oh, wow, that is a very steep hill. So we can see that relationship rather quickly. However, we don't see that oftentimes when we graph. Now, what happens after we get to the top? Well, it starts to turn negative, right? And negative. So when we get to 9/5, what happens? We're negative side. All these are negative values. This is a negative slope. And does it start off super sharp? No. It starts off very slowly, and then it works its way towards steepness as it goes here and works its way down. All right? Now, the acceleration is just a horizontal line at -10, because when we take the derivative of a quadratic, we get a line. When we take the derivative of a line, we get some linear function where there's some x and y exchange. Here, it's just one straight horizontal line with respect to its x values. Okay? Go ahead and rewind that, check it out. I know it's a little bit new for us, but that is the position, first derivative, and second derivative graphs. Hope you enjoyed. Thanks.